Good morning, everyone, and welcome to another live Quantser user webinar. In these webinar series, we highlight the work of academics around the world that use Quantser solutions and technologies. My name is Mshad EV. Together with my colleague Gemma Wang, we will be your hosts and moderators this morning. Today, we're very excited to have Dr. Vinodh Kumar from Vellore Institute of Technology, India, or VIT. Dr. Kumar will show how he and his team have used deep reinforcement learning control to do reference tracking and vibration suppression on the Quantser rotary flexible link system.
Thank you, Mitch, for the introduction. Hello, everyone. Thank you for joining this webinar. First of all, I would like to share my screen and confirm that it is visible. Is my screen visible?
Yeah.
Yeah. Thank you, Gemma. All right. Okay, so the topic of my presentation is deep reinforcement learning control for a rotary flexible link system. So for the next 30 to 45 minutes, what I'm going to explain is how we have implemented the deep reinforcement learning control framework for vibration suppression and tracking of flexible link system. And this is how I have framed my talk. Initially, I will touch upon the overview of machine learning and its types, and then I will discuss the reinforcement learning framework and the key elements of reinforcement learning and the reason for turning to deep reinforcement learning and what is the workflow. And subsequently, I will touch upon a class of reinforcement learning algorithm called deep deterministic policy gradient algorithm and how that algorithm has been applied for rotary flexible link systems. And then I will also finally brief about identifying the mathematical model of a flexible link through system identification technique and the hardware in loop testing of deep reinforcement learning on RFL system. Okay. So let's start with the overview of what this machine learning, because this reinforcement learning is a branch of machine learning. So it's a good idea to understand what the machine learning is and how it is interconnected. We know that the machine learning is a branch of artificial intelligence and it focuses on use of data to develop a statistical model that can learn from the data or previous experiences. In fact, the machine learning is widely used in several applications ranging from healthcare, self-driving cars, face recognition system, speech recognition, product recommendation systems, etc. Hence, the machine learning algorithms can generally be categorized into three different groups. They are supervised learning, unsupervised learning, and reinforcement learning. First, let us see what are the key differences or what is the mechanism on which these three learning algorithms work. Okay, so in the case of a supervised learning, the models are generally provided with the labeled data. That is, each of the input data is assigned with the label. And here the goal is to train the machine learning model in such a way that it can identify the patterns in the input data and then perform the classification. For instance, when you refer to this diagram, you can notice that, say, a machine learning model is given with a set of images containing different fruits, then the machine learning model is generally trained based on the shape and color and size of the fruits. And later, when the machine learning model is given with an unseen data, it should have the capability to predict the type or the class of the given input test data. Hence, the supervised learning can generally be used for three different applications, such as performing classification or object deduction or regression. If the input data is categorical in nature, we use that for classification. And if it is of continuous in nature, we can use it for regression application, wherein we do the prediction, such as weather prediction, etc. So one important point is that in the case of a supervised learning, it is based on the concept that the machine learning model learns by examples. And the second class of machine learning is the unsupervised learning, wherein the models are trained with unlabeled data. Unlike the previous case, here the input data are not assigned with any labels. So the machine learning model is expected to identify the underlying patterns in the input data and then cluster them according to the different patterns present in the input data. So this kind of unsupervised learning can be used for clustering and dimensionality reduction applications. Whereas the third class of machine learning is the reinforcement learning. It is a feedback-based machine learning technique. One key difference between the supervised learning and this reinforcement learning is that in the case of supervised learning, we train the machine learning model with assigned in output data that has a label. Whereas in the case of a reinforcement learning, the agent which is expected to reach a goal or meet an objective is expected to get trained in a stochastic environment. Hence, in the case of a reinforcement learning, this approach follows the principle of learn from experience, whereas the supervised learning follows a concept of learn from examples. So generally, this reinforcement learning is used to solve sequential decision-making problems. And majorly, it uses the concept of trial and error interaction. So in any reinforcement learning framework, there are two important entities. One is an agent and another one is the environment. So the goal of the agent is to ensure that it receives a maximum reward from an environment by set of actions. So when an agent takes an action and it is going to make some changes in the environment, then the agent will observe the state of the environment and it will also receive the feedback in the form of a reward. So the goal is to maximize the reward that the agent gets so that the uh, objective of the RL framework can be met. One key difference we can observe here is that in the reinforcement learning framework, it follows a concept of delayed feedback. For instance, for each of the action that the agent takes, it's not going to immediately get the reward. Rather, it is about the reward that it gets in the subsequent actions or the rewards that it gets for the given problem. So the goal here is to select a set of actions that can maximize the future reward. So just one simple analogy that we can mention here is that if a child learns to walk, initially it may fall down and probably learn the behavior of how to stand and probably take a step forward. So when it takes a step forward, it receives a positive feedback, probably in the form of a clap from the people around it, or probably if it falls down, it learns how it has to adjust its learning patterns so that it can improve its performance. Another one simple example that we can easily relate is the mouse maze example. Consider in a the mouse maze environment wherein the mouse is an agent and the goal here is to ensure that the agent gets more number of cheese that are put in the maze. So when an agent takes a step forward for each of the actions that it takes, it's not going to immediately get the reward. Here, the reward meaning probably getting a cheese that is placed at different places on the maze. Hence, it is the set of actions that's going to ensure that the agent gets more number of cheeses that are placed in this environment. Hence, a formal framework can be something similar to this. Generally, there are two entities. One is an agent and another one is the environment. So at any time step t, the agent takes an action and it makes some changes in the environment. So agent gets an opportunity to measure its state, and when it takes an action, it's going to make some changes in the environment that can be observed in the form of a states. And for the actions that it has taken, the agent is also going to receive the reward. The goal here is to ensure that the sequence of actions that the agent has taken has resulted in maximum reward, so that the goal of the reinforcement learning technique for the given problem can be achieved. Hence, it's generally used for sequential decision making problems. And another one simple example is that in the case of a robotic application, say if it is a pick and place robot, then the robot is expected to perform a series of actions, such as moving an end effector from one position to the other, picking an object and placing it to some other position. So here the end goal is that the position of the object should be precise with respect to the target. Hence, the robot can be trained in such a way that it learns, what kind of action it should mimic, so that this task can be uh, effectively performed. Hence, generally in a reinforcement learning framework, we can, identify some of the important, parameters, such as one being the agent and another one being the environment. So for each of the action that the agent has taken, it's going to receive the observations or the states. And according to how good the actions are, the agent will receive a reward. So it works on the principle of reward or punish mechanism. For each of the good actions that the agent has taken, it's going to receive a reward. If the action is not moving towards the goal of the system, then it is going to receive penalty. Ultimately, we are going to identify a policy, which is probably a set of actions, so that the goal here is to ensure that the agent receives the maximum reward. So the important terms in this context of RL are the agent, which is an entity that can explore the environment. And it should be noted that it's on a trial and error interaction. The agent does not have a prior knowledge of the environment in which it's going to work. So it has to explore the environment and learn what should be the good policy, so that it can achieve the goal. And anything outside the agent is treated as the environment. And the moves that the agent has taken are called action in the context of RL. And the set of observations are treated as the state. And the feedback it receives from the environment is the reward. So it can be a positive reward or a negative reward. For each of the good moves it has taken, it will receive a positive reward. And if the move is not in the direction of achieving the goal, the agent would receive a negative reward. And based, it's all about identifying or computing the maximum reward. So to do that, we have a policy mechanism in RL, and its role is to map the states to the actions. So as mentioned here, when we say learn from experience, the experience is basically a set of entities such as the observations, rewards, and actions. Hence, the state at any given time step t is basically a function of the observations, reward, and the actions the agent has taken. And there can be of two different environment. One is fully observable system and another one is partially observable system. In the case of a fully observable system, the agent gets the full state information, whereas in the case of a partially observable system, it does not have the full state information about the changes in the environment. So when we relate this to some of the control problems, just for easy understanding, this is one example of caught pole system. Here the goal is to ensure that the pendulum is vertically stabilized. And what are the different states that we can measure here are probably the pendulum angle and the pendulum velocity, and in a similar way the caught position and the caught velocity. And in terms of the action, when we notice, it is the amount of force that is applied to the caught system. So whenever the pendulum is vertically stabilized, then it is going to receive a positive reward, whereas when it falls down, it's going to receive a negative reward. So the RL has to basically figure out what are the good actions that has resulted in this pendulum being in upright position. Likewise, when we relate this to another application, say a robot locomotion, wherein the robot is expected to walk, then here the goal is to make this robot move forward, and some of the states we can measure here are the angle and position of the joints. So for which the action that is to be performed are the torque applied on the joints. So whenever it makes a forward movement, it receives a positive feedback, and when it falls down, then it's going to receive a negative feedback. So it's about identifying what are the set of actions that has resulted in positive reward, so that it can store that state action pair and improve upon the experience. So in general, the oral problems can be formulated through a Markov decision process, because all the states in oral has of all follows Markov property. What this Markov property is? So according to Markov, the future states depends only on the current state, and it does not require the history. That is, it does not depend on the past data. Hence, in MDP, a set of tuples are used to formulate this oral problem. They are S, which is a set of possible states, A, set of possible actions, and R being the distribution of reward, and P being the transition probability, and gamma being the discount factor. So we'll see the importance of this discount factor shortly. Apart from the agent and environment, there are four key elements in a reinforcement learning framework. They are policy, reward function, value function. Again, the value function can be of two types. One is state value function, another one is action value function, and finally, the model of the environment. Basically, policy is a strategy of how an agent should behave in any given state, provided it is given with the goal and its current state. Hence, it's simply a mapping between the states and action. So we can also view the policy as a simple agent's behavior function. Generally, according to the environment, there can be two types of policies. One is a deterministic policy and another one is the stochastic policy. In the case of a deterministic policy, the action is always same, irrespective of the instant at which it is attempted. Whereas in the case of a stochastic policy, it is the probability of the action that it can take, provided the given current state. Then the importance of the reward function is that, so it basically decides the what are the good moves and what are the bad moves of an agent by assigning the reward to the actions. The next important term here is the value function, which basically measures how goodness of a state, that is, it explains how rewarding it is to be in a particular state through a particular action. And this value function is basically computed through a mechanism called a future reward, which can be represented mathematically as, say, GT, which is the summation of set of discounted future reward. This can be represented as, say, R of t plus 1 indicates it is the reward that the agent would receive at time step t, and t of t plus 2 is the next reward that it would receive. Here, the factor gamma is the discount factor. So this can also be represented as sigma k running from 0 to infinity, sigma of k, so r of t k plus 1. Here, the importance of this discount factor is that when this is set to 0, then the agent is interested only in the immediate reward, not in the long-term reward. That is, uh, when the discount factor is less, it's more focused towards getting the immediate reward. Whereas when the discount factor is set to 1, then the equal weightage is given to all the rewards. So generally, this factor decides according to the importance that should be given to the rewards that the agent receives. So here the goal is to compute the state value function, which can be denoted as V phi of S. So the V phi of S is basically the total expected reward for the given set of states. And the second important term here is the Q value function, which is also called action value function. The action value function is the value that the agent gets for being in the current state and taking the action A of t, which is also the expected total reward based on the policy phi. And this Q function can be decomposed into a Bellman equation. Basically, this Q pi of is the function of state and action. And this Bellman equation can be viewed as two different parts. One is probably the current reward, and the second one is the discounted future rewards. So here the goal is to find out the optimal value function, which is the maximizing the Q value. Hence, the maximum Q value, if it is represented as Q star, then the optimum value can be represented as Q pi of star. So once the optimal value function is identified, we can identify the optimal policy by computing the argmax of this Q value function. Hence, the Bellman equation gets translated into this form. Generally, there are three types of RL approaches. One is value-based reinforcement learning, and another one is policy-based, and the third one is model-based. In the case of a value-based RL, the goal is to learn the value of the states and actions. One simple example for a value-based RL is the standard Q learning or DQN, which expands to Deep Q network. In this case, we compute the value for each of the states, and accordingly we update the Q value function. Whereas in the case of a policy-based reinforcement learning, instead of computing the value, we directly look for the optimal policy. Hence, here the goal is to optimize a policy that can result in maximum cumulative reward. Example for a policy-based reinforcement learning is a policy gradient algorithm, which basically attempts to map states to the action. And another class of RL is the model-based reinforcement learning, wherein an explicit model is used to train the agent, and according to the model, the further actions of the agents are planned and it is implemented. So these are the some of the basic terms or the framework of reinforcement learning. Now let's understand why we turn to deep reinforcement learning. What is the need for this deep part of this framework? Generally, in the case of reinforcement learning, what happens is like for each of the state and action, the value which is called Q value is computed and that is stored in the Q table. When the set of actions increases, when the number of state increases, then accordingly, this number of entries in the Q table is also going to increase. So for a complex system, computing state action Q value for a different state actions is, it's not feasible. Hence, instead of using a lookup table, something like this, we turn to another approach called, in the form of using a deep neural network. That is, here the deep neural network is going to act as a function approximator, which actually maps or which actually computes the what would be the Q value for a different state and action pair. Hence, this deep in this case refers to the application or utility of this neural networks. Here, the goal is to train an agent which can solve tasks which are which the human can solve. In this case, these neural networks are going to act as a function approximators. And this deep reinforcement learning is basically a combination of reinforcement learning and the deep learning networks. Here, the reinforcement learning defines what is the goal of the given task, and the deep learning is going to provide the mechanism for solving the given problem. Specifically, the deep neural networks can be used here to represent three different components of this deep oral, such as it can be used to represent a value function or a policy or obtaining a model. So, in fact, there are many similarities between these reinforcement learning frameworks and a feedback control, since it's about how one can apply deep reinforcement learning for addressing the control problem. I just would like to also touch upon the similarities between the reinforcement learning and the feedback control. So what we see here, of course, this is from math work, wherein an example is motivated through this comparison. All right, let's take a look at these two framework and see what are the similarities. So this is an example of a simple feedback control, and this is the RL framework. So here the RL algorithm that we use here to update the policy is something equivalent to adaptation mechanism in the case of a feedback control, wherein the controller parameters are updated according to the dynamics of the system or the measured quantity. Similar way, the term reward in the reinforcement learning is equivalent to error or cost function. For instance, if you consider, say, a linear quadratic regulator, the goal is to minimize the objective function or the fitness function so as to achieve the optimal, performance in terms of minimum control effort and, accurate tracking. So something similar to that in the oral framework is called a reward, wherein the objective is to achieve maximum reward, which ensures that the agent has achieved the goal. And in an oral framework, the actions taken by the agent is similar to the manipulated variable in the case of a feedback framework. And the measurements that we do in the case of feedback control is equivalent to the observations that the agent takes from the environment. Similar way, the environment is equivalent to the plant or the system that we are trying to control. And altogether, this policy can be equated to the controller. Hence, there are many similarities between these two. Now we will see what are the different phases of this oral implementation. So the workflow is something like this. So we generally identify the problem for which we would like to apply this RL. Of course, it's worth applying this reinforcement learning for a complex problem if certain problems that can be addressed through conventional control techniques, then it's preferred to go with the conventional approach. Whereas in the case of a complex problem wherein we would like to address constrained multi-objective problems, we can think of employing reinforcement learning. So the first step is to create an environment wherein the agent can get trained and define a reward mechanism, like what are the actions of an agent that should receive a positive reward and what are the actions that should result in penalty, etc. So we need to define a reward function, and then we need to create an agent and train the agent according to the reward function that we have set and the environment that we have created. Once the agent has been trained, it can be validated, and once the validation is successful, the policy can be deployed for the final evaluation. Okay, so when we look at the classes of this deep reinforcement learning, they can be categorized into two different groups, basically a model-based and a model-free deep reinforcement learning framework. And further, this model-free deep reinforcement learning framework can also be classified into two types. One is a value-based and another one is policy-based. Specifically, here I will just touch upon one class of this policy-based. In fact, not a policy. It's a combination. It's a actor critic based, deep reinforcement learning algorithm called DDPG, which expands to deep deterministic policy gradient algorithm. This deep deterministic policy gradient algorithm is an off-policy technique, and it is based on actor-critic structure. That is, it utilizes a couple of networks to train the agent. Generally, this DDPG algorithm is implemented to address the control problems which have continuous action space. So generally, there can be of two action space, one can be of discrete and another can be of continuous. So for addressing the control problems in continuous action space, we can go for, say, DDPG or PPO, which expands to proximal policy optimization, etc. One of the key features of this deep deterministic policy gradient is that it simultaneously learns the Q function and the policy. So for the implementation, this DDPG has two networks. One is an actor network and another one is the critic network. This is the framework in which the DDPG is formulated. Basically, DDPG consists of two different networks. One is an actor network and another one is a critic network. For realizing the continuous control action, it basically follows three important tricks. One is the action is added with a stochastic noise so that it can explore the environment. And the second one is it uses a replay buffer mechanism wherein the transitions are stored and the mini batch from the replay buffer is used to train the agent. The reason is that generally in optimization problems, we want this data to be independently distributed. So in order to ensure that the state transitions are stored in the replay buffer and that is used to, and the sample out of it is used to train the agent. And the third important feature followed in the DDPG is that it takes a copy of the actor and critic network called target actor and target critic, which is to basically ensure the stability in the learning process. Instead of directly updating the actor critic, the target actor and critic are updated based on the performance. The main actor and critic network are updated for realizing the given policy. So generally in the actor network, the role of the actor network is to take an action for the given states, whereas the critic network is to compute the goodness of the action in the form of a Q value. So this is the actor critic based feedback implementation. So the actor network is going to implement the policy in the form of a control action. And according to the action that it has taken, the critic network is going to evaluate how good the actions are. And the critic network is going to update the policy of this actor network. That is how it is implemented. Now, I'll just quickly touch upon how this DDPG is being implemented for a, rotary flexible link system. Before that, quick overview of this DDPG pseudocode. First, we initialize the critic and actor network, and we take a copy of that to initialize the target networks as well. And the agent takes an action, which then we actually measure the states and receive the reward and store it in the replay buffer and take a sample from the replay buffer and then compute the target values based on the discount factor. And subsequently, we minimize the loss function and update the critic policy network. Then we actually perform a gradient ascent so as to maximize the reward. And finally, we update the target network based on the soft target update. Here, the tau is the learning rate. Now, I'll quickly touch upon how this is actually implemented for a rotary flexible link system. So this is the schematic diagram of a rotary flexible link system, wherein this system consists of a servo motor attached with a flexible link. This system consists of two sensors. One is an optical encoder and another one is the strain gauge. In terms of the control variables, VM, the motor voltage is the manipulated variable, and the controlled variable are the servo angle theta and the deflection angle alpha. The goal of the system is to ensure that when the servo tracks the set point profile, the tip deflections at the tip is as minimum as possible. Okay, so this kind of system is often encountered in light space structures, including robots and spacecraft. So the control goal here is to ensure that the servo tracks the reference trajectory. While doing so, the vibrations in the flexible link is as minimum as possible. So first of all, for identifying the empirical model of this rotary flexible link system, we have implemented a model predictive control and capture the input and output data. First of all, we have gone for the closed loop identification because the open loop model of this RFL is basically an unstable system. Hence, to identify the empirical model, we have gone for the closed loop identification, particularly a direct approach. Reason is that the direct approach does not require the knowledge of the feedback. So we capture the input data, which is the motor voltage, and capture the output variable, which is theta. That's the servo angle. So this plot shows the input output data. The top one is the servo angle and the bottom one is the input data, which is the motor voltage. And the bottom plot shows the spectral plot of the input and output data. So from the top plot, we can notice that the rotary flexible link exhibits low pass filter characteristics. So having identified the nature of the system, we have attempted to uh, design empirical model, specifically auto regressive AOX model. And we perform three different tests to validate the goodness of the model. The first one is the test for the deterministic model. The second one is the test for the stochastic model. And third one is the cross validation. Particularly for the deterministic model test, we have computed the residuals and obtained the cross correlation plot between the residuals and the inputs lags. From this, we can notice that none of the residuals is beyond the threshold. Hence, we can ensure that the model has managed to uh, capture the deterministic part of the system effectively. Similar way, the second one shows the autocorrelation function. Except at the zero lag, other input lags does not have any significant correlations. Hence, we can note that the model has managed to capture the stochastic part. And then to validate the model, some unseen data is given as an input to test whether the model is able to predict the output. We can notice the blue one is the test data and the dashed red line is the model output. We can notice that the model has managed to predict the output pretty close. So this is the OX model that is built based on the input and output data. And for performance comparison, we have also implemented a model predictive control with a sampling time of 2 milliseconds and the prediction horizon being 20 steps and the control horizon being 2 steps. And the additional constraints considered in this implementation are: one is the hard constraint, that is the motor voltage should not be beyond 10 volt. And another one is the soft constraint, which should ensure that the deflection angle is well within 5 degrees. And these are the configurations for the deep reinforcement learning framework. So this is also implemented with the sampling time of 2 milliseconds. And then the stopping criteria followed here is the episode reward, and it has been trained for a maximum episode of 1000. And this shows the actor critic framework for the DDPG. So the actor network is going to take the set of states. In this case, the states are the error, integral of the error, and it's going to result in the action in the form of a motor voltage. So 5 fully connected layers are used in order to generate the action, both in the critic and the actor network. One key difference that we can notice here is that for computing the Q value, the uh, uh, fully connected layer is used in the case of a critic network, whereas in the case of an actor network, the final layer contains a fully connected network along with the tangent layer, so as to restrict the action or the motor voltage well within the constraints. And this shows the reward function, which is basically a quadratic reward. When the agent takes an action, and if it ensures that the error is minimum, then it receives a positive reward. When the error is more, it's going to receive a negative reward. So this reward function is separated into two different parts. One is the servo penalty, another one is the tracking reward. So it's trained in such a way that when the servo angle is beyond plus or minus 45 degrees, then it would receive a negative reward. Whereas when the tracking is pretty close or the error is minimum, then it would receive a positive reward. And this is the Simulink diagram wherein the RL is implemented, the trained agent is configured here, and the performance is tested. And this shows the experimental setup or the connection diagram. So the RFL system consists of a couple of sensors, optical encoder and a strain gauge. The optical encoder is going to measure the servo angle and the strain gauge is going to measure the deflection angle. And the interfacing is through Q8 USB DAC board. And based on the RL algorithm implemented in the computer, the control action is generated and it is fed to the RFL system through a power amplifier. And we have tested the performance for 5 different test cases. One is the nominal trajectory tracking, wherein a square reference profile of plus or minus 30 degree is given as a set point. And we can see the response of a model predictive control and the reinforcement learning controller here. The blue dash line is the model predictive control response, and the red dash line is the reinforcement learning controller response. we can notice that the reinforcement learning control response is smoother compared to the model predictive control response, particularly during the steady state. The when we analyze the response of the vibration, we can notice that the vibration at the tip is much less in the case of reinforcement learning controller compared to the model predictive controller. And this is the amount of control input supplied. We can notice that the amount of input taken by the RLC is lesser than that of the model predictive control. And the second test case here is the dynamic velocity profile. So when it is given with an increasing amplitude, we can notice that compared to the model predictive control, the amount of deflection at the tip of the RFL is much less in the case of RLC. And to assess the regulatory performance, two different disturbances are tested. One is a short disturbance wherein a pulse signal is given as an input and the deviations in the controlled variable are shown here. We can notice in the case of external disturbance, there is a slight deviation in the case of a model predictive control, whereas the deviation is much lesser in the case of a reinforcement learning control. And this is the corresponding deflection angle. Similar way for a continuous disturbance, when a disturbance signal of sinusoidal pattern is given, we can notice the deviation in the RL is much lesser compared to the model predictive control response. And the final test case is assessing the performance in the case of varying payload. An additional payload is attached to the tip of the link, and the performance of the MPC and RL are tested. And this shows the tracking response of MPC and RL. We can notice that the deviations shown in the form of a blue line is for the MPC, and the red one is for the reinforcement learning controller. And we can observe that the deviation is much lesser in the case of reinforcement learning control and compared to the model predictive control. So the performance is finally quantified through a factor called root mean square error. And in all the 5 test cases, we could notice that the deep reinforcement learning control performs better compared to the model predictive control. And this bar chart shows the root mean square error for the 5 different test cases considered in the study. So I just also would like to play one simple video which has been recorded while conducting this experiment. And in the interest of time, I'll quickly run through this video. So this is the experimental setup. As we can notice, this is a flexible link which is interfaced with the computer through a Kuwait USB DAC port, and the servo motor is driven through this volt-pack amplifier. And so this shows the connection diagram. So first, this is the response of the model predictive control. Both MPC and reinforcement learning control are implemented in Simulink. Here, the inset image shows the response of the model predictive control. We can see 3 different plots here. One is the deflection angle alpha, second one is the servo angle theta, and third one is the motor voltage. So for the model predictive control part, we can notice initially there is a considerable oscillations and the offset in the steady state. Whereas this is for the second case, that is the deep reinforcement learning. This is the trained RL agent. And now we will see the response of the RL for the same set point profile. We can notice here that when the deep reinforcement learning is is in action, the tracking is pretty smooth compared to the model predictive control. and this is the deflection angle. We can notice that the deflection is much lesser compared to the model predictive controller response. And this shows the amount of voltage given to the motor. All right. So in the interest of time, I just would like to close my presentation by mentioning what are the challenges we have to address while implementing this RLC. One such important challenge is appropriate selection of reward function. So according to the problem that we are trying to address, we need to formulate a correct reward function so that the agent can be effectively trained. And another key problem that we could notice is the convergence of these RL agents during the training, because the appropriate hyperparameters need to be set so that the convergence of this RL can be guaranteed. And finally, we also should ensure that this reinforcement learning results in the output which is practically realizable and it's reliable. Moreover, we should also ensure that it results in a stable response. So there is another framework which is also being explored, kind of safe RL, wherein the output of the RL is also tested for its ability to realize safe environment. With this, I complete the presentation and thank you for this opportunity. And if there are any questions, I will be happy to answer.
Thank you so much, Dr. Kumar. That was a great presentation. Really appreciate it. So I think, as you said, we can proceed to the questions. We've had a few come in from the audience. So starting with Matthew. Yeah, he found your webinar very informative, and he would like you to explain a bit more about the approach that was followed that you used for building the empirical model for the Rotary Flexible Link.
Yeah. All right. So in this case, for building an empirical model, we have followed a closed loop identification technique, because the rotary flexible system is an unstable system in open loop. Hence, we cannot go for an open loop identification system. We have gone for a closed loop identification, particularly a direct approach, because it does not require the knowledge of the feedback, whether it is model predictive control or linear quadratic regulator. It doesn't matter. All we need is input and output data. Particularly in the RFL, the input data is the motor voltage and the output data is the servo angle. So by capturing these two data, we built an OX model to train the RL agent.
Okay, thank you. We have another question from Mr. Ali. He wants to know exactly what are the observation, what exactly did you use in the observation section? Was it the integral of error or just the error itself of the flexible link?
So in this case, we used both error and integral of error as the observations to train the RL agent. Because as we increase the number of states, the amount of information that we can extract will also be more informative, and it could be used to effectively train the RL agent.
Okay. Question from Lutz is he thanks you for the webinar and like to know if the RL agent was fine-tuned when you were using the hardware setup.
Yes, of course, we had to explore different, the impact of various hyperparameters in the DRL, particularly the learning rate and training it with different mini batch, etc. And after ensuring that it works in a simulation environment, we tested in the hardware in loop setup.
Okay, thank you. Another question from Tanju Lee. Also, thanks you for the presentation. And he wants, I want to ask you, I want to ask what you deem as an appropriate discount factor for continuous control applications, such as trajectory tracking.
So generally, the discount factor is set high so that more importance is given to the future reward instead of the immediate reward. Because if you consider, say, a game of chess, not each action is important. It is actually a set of actions that will enable us to probably win the game. Hence, generally, this is set in the range of say 0.9 to 0.99 when we tested it.
Okay. One question from Jing Wang for DRL learning control, how to determine how many layers in the neural network you will use in the control design.
So in this case, we have gone for 5 different layers for both critic and actor network. So the more the layer, the more the computation is. So, we empirically tested it on a hardware platform and then chosen that 5 layer would be sufficient to train the agent.
Okay. One question is, okay, so you chose the what's known as a deterministic policy gradient, right? So
Yes.
why only DDPG algorithm is chosen? Why not another technique?
Yeah. So generally, the DDPG algorithms are used to address the control problems in continuous action space. Particularly, the system we considered in the study is a rotary flexible link system, wherein the actions are continuous in nature. For example, say it's in the form of a servo angle or the motor voltage. As it is a continuous action space, we have gone for a DDPG. And of course, we have also explored another algorithm called PPO, which stands for proximal policy optimization.
Excellent. Well, I think that's all the questions we have. Thanks, everybody. So this brings us to the end of our webinar. Again, we'd like to thank you again, Professor Kumar, for the great presentation and for everybody that attended. Please visit us on quasar.com as well and our LinkedIn page to find out about our systems and any other upcoming webinars. Have a great day.